directly and going to the discussion and questions at the end, just to be more or less on.
Okay. Okay. Probably I should. I'm sorry. Let me clarify my throat. So good afternoon to everybody. It's a pleasure to share this symposium with you guys. I'm really grateful for the talks of the three, starting with Grzegorz and Tommaso and Thomas. I think that I'm learning a lot, and that's my time to learn, because for a long time I've seen your works and I'm busy trying to do my own, and I don't know if that happens to you, but anyway, I sort of apologize. But then the idea of this meeting is precisely to start to talk to each other about I'm sorry, about this common topic. So let me start by sharing my screen. Let me see. And probably now you see my screen. Am I right, Luis?
Yes, I can.
Okay.
I guess everyone.
And then how about my presentation? Can you see that, the first slide? Okay.
Yes, I can.
Great. Okay, then let me start. I will try to restrict myself to 25 minutes, so that means that I will not finish my talk anyway. But the first assumption is that we would like to really have this exercise of communication. And let me say, I will talk about a different theory, let's say, in several senses, mostly on the fundamental basis, but in the end will be a theory that talks about the same phenomena, let's say, among other things, glass transition and gels and so on. And this is referred to, let me start by introducing this theory. Let's say the acronym non-equilibrium self-consistent generalized Langevin equation, and the acronym in blue. We haven't coined a better acronym, so please bear with me. And what I want to do is to explain to you in these 25 minutes what this is about. And the first thing that I want to tell you, that it is sort of, I remember once, Grzegorz, that you made a comment, and I really want to recall it. That's sort of a calculation box. It's nothing, I mean, as opposed to something that you want to be able to understand things fundamentally. And in fact, it is a calculation box. And so the first impression that I want to give you is a calculation box that is a very useful one. And I will start with a brief review of the results that you can predict with this set of equations whose solution constitute this calculation box. And then I will go, okay, but now explain what is inside this box, what is, let's say, the fundamental basis. And I left now to the end that the basis is a non-equilibrium version of ONSAGER-MACHLUP theory of, or ONSAGER's theory of fluctuations and irreversible processes that we made an effort to extend or to propose an extension to non-linear non-equilibrium conditions. But if I start from here, the group in San Luis Potosí heard my talk and said, don't start with that. So I left that to the end. And instead, I will tell you first roughly what are the main ideas that are behind or inside this calculation box. So let me start with the first one. And let me start by saying that if you have a simple, let's have in our mind a simple model system like Lennard-Jones fluid, where you know the phase diagram, that it has gas, liquid, coexistent, solid, blah, 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 and that you understand that by going to your statistical mechanical course, you were taught how to calculate the equations of state, phase diagrams, and so on, starting from the Hamiltonian, from the pair potential in this case. And we also talk about processes, but we say, but please do the process very slowly so that you can go from equilibrium to equilibrium states. And then if you go from liquid to a solid, you have a beautiful crystalline glass. Now, if you say, oh, but in practice, I actually would like to do it very quickly and go home or go to the movies or whatever, then it may be that you don't get this and instead you get a glass. And if you do that also inside the spinodal region, you know that the system will phase separate and through a spinodal decomposition process. But if you do the process even further, then this full separation will get arrested in between. These are simulations by Testarder, and Cobb with the Lennard-Jones fluid. And if you go even deeper, the process of arrest starts to show up even earlier. Okay, the fundamental point of view from our side is those phenomena cannot be explained by pulling, let's say, the machinery that we know from equilibrium statistical thermodynamics. This is like the first postulate of our attitude. And instead, we would like to have something like an extended version of equilibrium statistical thermodynamics, where you, let's say it would be a similar black box where you put in the Hamiltonian, but now you should also put the protocol of preparation of your system, and then get as an output the response of the system in terms of equations of state, the structure, dynamics, and so on. That would be the idea. And the first message that I want to convey is that this black box is really, let's say, the non-equilibrium self-consistent theory that I will show you at the beginning is sort of a first version of this black box. And let me introduce those, let's say, this will be something like a generic theory of irreversible processes in liquids. And let me go directly to show you, let's say, well, this was published 11 years ago by Pedro Ramirez and myself in this paper. And basically, the end result that I want to show from that is this calculation box, which consists, let's say, whose solution will, describe the formation of glasses and gels and so on. And how it looks like, this black box from the inside, is a set of equations. One of them is an equation for the time evolution of the structure factor, the ordinary structure factor that you would measure in light scattering. But when you quench a liquid, let's say you keep it, our Lennard-Jones liquid, you keep it at a given density, and it was at a given initial temperature, and all of a sudden you quench it down to a lower density. And then the time evolution of the static structure factor, of the structure factor, will be governed by this equation. And this equation requires this mobility, which is the local and mobility, let's say, in time during this irreversible process. And then if you had this function, then you would get the structure factor, and then you will also input this in a black box, which is basically like equations of the sort of MCT. But it's, let's say, I will come to the details about this. And from this, you will get the dynamic properties, which one of them is this B of T that you need to put back. So if you want to see it as a calculation machine, there is no problem at this point. Because what I want to show you is that, okay, this is a well-defined set of equations. And now you put in the pair potential. I will explain later that it enters through the calculation of this object, which is the second derivative of the phi energy, the final temperature that you quenched. And that is like the driving force, this difference. So let me show you. You give the pair potential, you give, let's say, the protocol, and that means the initial and the final temperature. And now you solve this set of equations, and you will have the full time evolution of the static structure factor and all the dynamics that enter here. Okay, so okay, this is what is inside this toolbox. We will explain later where it comes from. And now for this 11 years, we have already reported the solution of these equations under several circumstances. I cannot go into details, but let us imagine, let's say that we apply let's say we solve that for the Lennard-Jones system when you go to high densities and go from the liquid to the solid, let's say, solution. And then this is an example of the type of results. The solid lines would be the theoretical predictions. The symbols correspond to the computer simulations in which the alpha relaxation time plotted as a function of waiting time saturates, like Thomas was saying. But in this case are the same data, but now with the theory that I just mentioned. With this set of equations, the solution are plotted here as solid lines. And there are let's say, for example, the prediction of the theory, when you go deep enough beyond the MCT transition line, it tells you the whole story, how this correlator looks at different waiting times. And it depends, let's say the waiting time depends, I'm sorry, the alpha relaxation time depends on waiting time. And if you plot that in this case, as also Thomas reviewed it, in this case, the theory predicts that it will increase indefinitely. And I will not go in more detail. Now you can take, let's say, soft spheres and do quenches in temperature, and you get basically the same scenario that was described by Thomas. And you can put it this way. Let's say you have two regimes, equilibration and aging, and all of this scenario comes by solving this set of equations. These are some of the references where these results are reported. Now, you can also go to more complicated systems like mixtures. And in the case of mixtures, for half-sphere mixtures, it's just a short review, so I will go very flashy. You can calculate this, the phase diagram in terms of the volume fraction of the two species of hard spheres, and then the theory predicts, very much like mode coupling theory predicts for the case of mixtures, the existence of mixed states or hybrid states in which, let's say, the big particles are arrested, but the small particles diffuse, and here both are arrested, both are diffusing. The same theory has already been tested with respect to the simulations and experiments. And let me only say roughly that the three approaches to the same phenomena seem to agree, let's say, experiments, simulations, and theory, the trends observed and predicted by the theory. And that is for mixtures, and probably I'm exceeding my time with respect to this review, but let me just mention that you can also go to the Asakura-Oosawa mixture and calculate the phase diagram in the plane of the concentration of both species. And then you have a spinodal region, and you have more bizarre predictions that besides the formation of these mixed states here along this line that borders the equilibrium fluid, and that's, let's say, comparable to the experimental data that people measured for the Asakura-Oosawa, the colored polymer mixture. And let me also mention that if you go to a completely different regime, still with the Asakura-Oosawa mixture, but now the polymers and the particles, the colloidal particles, are sort of similar in size. Then the theory predicts a funny phase diagram with mixed states, this number 3, but which is a very funny mixed states, because now in this regime, it is not the colloid, the one that gets arrested, but it is the polymer. If you start to add polymer like this and enter this regime, along this process, the theory predicts that the diffusion coefficient of the polymer will go down, and the simulations tell you basically the same thing, whereas the colloid remains almost, this is sort of counterintuitive, and that's the reason why we published this, to show that the theory makes, at the beginning, not very intuitive prediction, but that can be corroborated with simulations. And what is happening is simply that the polymer are becoming segregated from the colloid. Okay, there are other applications, and let me finish this part of my talk by saying you can charge the system and have a bunch of different how to say, mixed states. In this case, for example, if you have a 1-1 electrolyte with a large size asymmetry, and the theory predicts that there is a region in a state space where you might have a very counterintuitive mixed state in which the big particles are the ones who remain moving, whereas the small ions are the ones who get arrested. And this has been checked in simulations as well. Okay, so I'm finished with the first part of my talk, trying to present you the self-consistent theory as a black box that is useful to calculate things. Now, what is inside? And let me tell you. Let us start by having again the same set of equations, and let us, let's say, take away this red box and see what happens with this portion. As I said, this is basically the set of equations that relate the static structure factor or writes the dynamic equations in terms, or the dynamic properties in terms of the static structure factor. And as a result, you can solve it for the dynamic properties. And as such, if what you input here is the equilibrium static structure factor, you get here the equilibrium dynamics. And that was the first version of the non-equilibrium, of the self-consistent theory that we built in the first decade of this century. And that is called simply self-consistent generalized Langevin equation theory. And this is the one which is sort of equivalent to mode coupling theory. Of course, the details in the equations they are different, but in essence, the box as a calculating tool is basically the same. So this is now what, but this one has the waiting time built in. What happens is that we didn't adhere to the projection operator type of approaches to derive the generalized Langevin equation. I will talk about a little bit later. And within the scheme, the fundamental theoretical basis based on Onsager's theory, we can derive these equations also for non-equilibrium stationary states and ultimately for non-equilibrium processes. So that's the origin of this part of this system. Now, what is the origin of this sort of the red box? Basically, let me, before saying what is the origin, let me say a few features that you get and which are already mentioned by Thomas. This equation, the relaxation equation for the structure factor, it has stationary solutions, and one of them, category is the one that makes this bracket 0, and those are equilibrium states. But this theory can also have dynamically arrested states, which are also stationary solutions of the same equation, okay? And this corresponds to the ordinary equilibrium states, and these ones actually, when we solve these equations and see the solutions that have this feature represent glasses, gels, and so on. And in fact, let me illustrate this immediately. If you quench the Lennard-Jones fluid deep inside the SPINODAL region and you solve this equation, we will see examples. Then it happens, if you do the simulation we saw already, you don't see that the system will equilibrate in a homogeneous state. That doesn't exist inside the SPINODAL. The only possibility that you have a statistically homogeneous state is, let's say, this other possibility. And if you solve the solution, if you solve the equations for this Lennard-Jones for a quench inside the SPINODAL and look at in simulations how the static structure factor looks like, there is this peak at wave vectors, there is small wave vectors like 1. The main peak, Hard-sphere peak, should be to the right at 6. And this peak at small wave vectors starts to increase like this, signaling the formation of clusters and so on. So this is a completely non-equilibrium behavior. And that has been very well documented in experiments and so on. And now, if you compare what is the solution of this calculation box for this specific example, you solve these equations, then the solid line is the prediction of the theory, and it follows roughly the behavior of the simulations. Okay, that means that this calculation box must be founded on something really solid. And let me say a few words about that. What is, let's say, the fundamental basis for that? I wanted to mention something that has to do with culture and language. As it happens, my PhD occurred in a chemistry department with Don McCord in Indiana. And then I went to another chemistry department with Joe Kaiser. As it happens, McCord knew about the static structure factors and this kind of business and at equilibrium. And Joel is one of the persons in the world who knew most about non-equilibrium thermodynamics. His book, I really recommend it. I learned a few things from him in those 2 years, but it took me many more years to really understand much of the advices that he has in this book. So anyone that wants to, from this ideology, from this chemist's ideology, chemists think about time. They cannot think only on the thermodynamic, the static, and this kind of the equilibrium world. They have to get out of that plane, and that means kinetics, and that's basically the fundamental basis. The first thing that one learns in Kaiser's book is ONSAGER's theory of linear reversible thermodynamics and of fluctuations, thermal fluctuations around equilibrium. If you learn that, and that I will discuss that in other occasion, there is no time yet. ONSAGER and MACHLUP actually they don't say it that way, but they actually use the mathematical model, a Norsten-Uhlenbeck stochastic process with a bunch of properties, and then they simply said the thermal fluctuations at equilibrium behave like that mathematical process. And if you see how successful that approach was, then what we did was to say, okay, is there a more general mathematical stochastic process, one which is no longer at equilibrium, but is only stationary, and even better, is not stationary, but is piecewise stationary. And then this is this briefest summary of such a model. And that model, the first moment of the stochastic process obeys a nonlinear equation. This would be the hydrodynamic equations, the full non-equilibrium nonlinear hydrodynamic equations, or the diffusion equation, or what have you. And this same, if we say that the fluctuations around this mean value obey, let's say, this piecewise stationary process, then the second moment, or the covariance, must obey this equation. And we might elaborate even further, but still, these two equations are the ones that I want to emphasize, because it is exactly these equations that we will now apply. And under equilibrium, we have to appeal to the stability, the linear stability, or Lyapunov stability of this nonlinear equation. And then that the assumed stability of the stationary state implies the existence of a Lyapunov function, which in our case will be the entropy, okay, or the free energy. Okay, anyway, there is a machinery that is based on a well-defined mathematical model of stochastic processes that we assume the thermal fluctuations around the non-stationary mean value will be described by such a model. And I will not say anything more besides that, but just to say that let us assume now that this guy is the local density of a liquid. And then we will have one equation for the mean density and one equation for the covariance, which in our case will be the static structure factor. And those equations are written here in full detail. This one, no surprise, this is just Fick's law. This is the electrochemical potential, which is the first derivative of the Lyapunov function, which is in our case the free energy or the entropy, let's say. And this is the second derivative of the free energy. So these two guys are thermodynamic properties. And if you have a functional, and let's imagine that we have random phase approximation functional for the free energy, then we know what to put here and what to put here. And in addition to this, we also have this object, which is this local mobility. This is the self-diffusion coefficient of the particles at any point in the system, at any time in the process. And of course, these are two equations for these two guys, the local density, the local structure factor, but it requires a closure for this object. Of course, that closure will be an MCT kind of set of equations that I'm not writing here. But anyway, those closures are the ones who will help us in solving this. Now, if we haven't solved this pair of equations because it's too complicated, and the equations are written and well, how to say, well defined mathematically, so they should be amenable to theoretical, I'm sorry, to numerical procedures. But instead of that, instead of fighting to have the full solution of these two equations, we argued as follows. Let us approximate the local density by the bulk density plus the deviations from heterogeneity, from homogeneity. To a large extent, I would identify this as Tommaso Rizzo's equation for the distance from the, well, not exactly, although this is not written as a distance from a given value, we could subtract that and put it here. But let's say you assume that you have a theory that gives you the mean field picture of this, and let's say the additional delta n will be we would like to have that would be the purpose of the first equation. But let's say, let us start by neglecting this guy. And then from these two equations, the first one doesn't tell us anything because the n will be a constant uniform, and so this goes away, and we are only left with the second, and the local density will become a control parameter. And then the second equation is the one who ends up being the equation for the static structure factor, and this is the origin of this equation that we used in our theory. Now, going back to these two equations, however, we might want to, general versus mean field. This is exactly what I meant to say. When we have the two equations, two equations that we have not solved, that would be the general non-equilibrium self-consistent theory. And its mean field version would be the one that includes this approximation of neglecting deviations from heterogeneity. I'm sorry. Now, instead of neglecting them, we might go back again to the first equation and say, why to neglect them completely? Why don't we linearize that equation to linear order in the deviations? You can do that. That can be done, and then you can solve the first equation as well. And let me show you, let's say, the results. If you do that, when you quench inside the SPINODAL region and look at visualize what is the solution that you get. Remember that what we should get is something similar to these images. And let me not go into much more detail. What these are, let's say, the same results, but now obtained purely theoretically. A shallow quench will lead to full phase separation. A deeper quench will get a rest at an earlier stage, and even deeper will go to will happen even earlier. And if you go to a different isochord, then the system will not evolve very far from the initial state. So this is roughly something similar to what these people in the simulations found. And how did we get that? By going back to the general theory, and although we still calculated the heterogeneities by linearizing in the heterogeneities themselves the first equation, but anyway, it provides something that you could even put in a video. This is one video that tells you how this heterogeneities leading to a gel look like. And if you notice, the first third of this time, the system does almost nothing. All of a sudden, it starts growing, and then it stops growing and does nothing. Let me show it again. We could talk about the physical meaning of these things. Finally, let me ask my chairman, how am I doing with respect to time?
You already consumed all your time.
Oh,
but if let's say you can take 2 or 3 minutes but in order to privilege the further discussion and
okay, let me. I actually had inserted this. Thank you very much. Number one, and that means that I will stop here because this is my time. We probably. It would be nice to have a discussion with the 3 speakers, but probably let me just say that with respect to this, if you give me these 2 minutes, let me use them by saying, what is the really fundamental basis? And I said, extending Onsager-MACHLUP theory. So what is Onsager-MACHLUP theory? Let us start by a mathematical model. This is, let's say, a multivariate stochastic process. We will talk about the deviations from the stationary condition. We assume this process to be stationary, and this is notation. And then the main definition of an Orsten-Uhlenbeck stochastic process is the one which is generated by a linear differential equation with additive noise. And you say that this additive noise is a white noise. That means that it is Gaussian, stationary, and delta correlated. And once you have said this, you have set all the conditions that you have to say to define the stochastic process delta A. And one of the main consequences of those assumptions is that the mean value evolves following this linear equation, and the covariance evolves following this equation. Now, you can, for example, look at the concept of stationarity by looking at the second equation and saying, imposing the stationarity condition, making this 0, and then you will get the fluctuation dissipation relationship. Let me stress that we are doing mathematics, no physics right now. And so let's keep this fluctuation dissipation relation. Now, let's look at the first equation. The first equation is a linear version of a non-linear equation, and then Lyapunov has something to say with respect to that. And that is that there must be a function of state whose second derivative evaluated at the stationary state must obey this relationship with the relaxation matrix, and with G being a matrix with some symmetries that, if you compare with the fluctuation dissipation relationship, clearly you can see that this G has to do with this gamma, the strength of the fluctuations. And let's say that the stationary covariance must be the inverse of the matrix of second derivatives of the Lyapunov function. This one we also keep it for later, but again, notice that we are talking about only, I'm sorry?
For later, but not very late, please.
Yes, I know. Just wanted to show you because this is cute. When you combine, let's say, the fluctuation dissipation relationship, another way to see it is that this product plus its transpose must be a symmetric matrix. That means that this product must have a symmetric part and an anti-symmetric part. And this simple reflection takes you from this way to write the relaxation equation for the mean value to this second form. Now, if you now take this second form and notice, let's say, that the inverse of the stationary covariance is nothing but the matrix of second derivatives of the Lyapunov function, or the first derivative of the first derivative, then you can use the chain rule here to end up writing this equation in the way it is written in the end here. And that is that is exactly the structure of the so-called linear laws of irreversible thermodynamics. And so that means that even the linear laws are already contained within the Orsten-Uhlenbeck stochastic model. And now what Onsager did was to simply say, let's take that model looks very good, and let's say the thermal fluctuations behave like that. And except that now we can identify the Lyapunov function is just the negative of the entropy or the free energy, what have you. And here is my second thank you very much, but only to say that if you relax some of the assumptions in this case, you can extend Onsager-Machlup or Onsager's, the spirit of Onsager's theory to go to the nonlinear regime, which is really the basis of the equations that we actually solve in the end. And with that, I apologize for taking so much time, and I thank you very much for your attention.
Thank you, Magdaleno, for your very nice talk. And now we have time for discussion, even though we are a little bit late, but I'm very happy that we are more essentially all of us remain here. So does anyone wants to raise a question regarding both Thomas and Magdaleno's contribution, on even Tommaso's and Grzegorz? I'm not seeing anyone. I think Grzegorz wants to ask them. No?
Well, okay, I have a technical question to Thomas. Integration through transients was introduced for shear perturbations. And shear perturbation is something that you actually put in the evolution operator. Now, what you are talking about is a quench, so changing the density of the system. This is not a parameter in the evolution operator. Does this cause any problems?
That's a good question, so the way I try to go around this is basically by saying that you could imagine something like a confining potential that is in the evolution operator and that you change. That's at least the closest I can think of in terms of a density quench.
But that's sort of an idea rather than
that's the I mean on the level where I say all I need is that I go from one to the other stationary state. Yes.
Okay, and I have an additional question. So if you recall, the long time ago, Arnold Flatz came up with Mott coupling-like equations for aging. How do your equations compare to his? What are advantages, disadvantages, etc.?
It's actually also a question that I continue to ask myself if I listen to Magdaleno, because it seems that what Arno Flatz has been trying to do is to tackle the full problem that you are out of equilibrium, you don't even assume fluctuation dissipation to hold. So you need to have coupled equations for the response and the correlation functions in a sense. And I think that, I mean, what I try to do on the basis of ITT is really inspired by Magdaleno's Onsager-like approach, where for me, but we can ask this to Magdaleno, for me, the main assumption there seems to be that you assume that the coefficients in the Onsager-like equation are local functionals of the current state of the system. And I think basically this is like cutting the Gordian knot that Arnold couldn't untangle. That basically by your approximations, you separate the two equations. So this is the more careful answer, saying in principle what Arnold did should be correct. With the small problem that he was using ideal MCT, and ideal MCT predicts a divergence that is not there. So his theory is the theory of what would happen if you could attain the ideal glass and it would age. So that kind of limits its applicability. It could, so this should be correct. And what Magdaleno and I are basically doing is to decouple the equations by hand by some approximation. To say
so go ahead.
We decouple into an evolution of the one the one-time quantities, and we only worry about correlation functions. We don't even worry about the fluctuation dissipation theorem or the response function that you would have there. It could be that the deeper answer is in looking carefully how you define the non-stationary out of equilibrium correlation function. And I think these so-called transient correlation functions that appear in ITT, they are mathematically well-defined, but you have to be very careful in claiming that they are the ones that you actually measure in a computer simulation. There are various indications that you can have subtle differences there. And we looked at this recently for active particles. But it's still not fully understood, I would say.
Okay, thank you.
Is there any other question? I think Matthias Fuchs has raised his hand. So please, Matthias.
Yeah, connected with, in a way, this question and asking Magdaleno and Thomas, and especially Magdaleno, because he also considered the average density, which is in a way, on the one hand side, a topic of dynamic density functional theory considerations there. And on the other hand side, I was wondering if you quench close to, in the two-phase region there, I would also wonder the connection to time-dependent Ginzburg-Landau theory and those long wavelength approaches that have been well used and well studied. How does the approach to the density profile, or then on the second level, the approach to the time-dependent, the aging structure factor, how does it connect to those approaches, density functional theory or time-dependent Landau-Kahn-Hilliard theory?
Let me try to say with words only. You remember we had two equations. One of them was for the local density, and that was basically fixed law. But let's say if it included this local mobility function B of R and T. If you said that B equals 1, that is exactly the density functional, the basic equation of density functional theory. Okay. Now, on the other hand, if you go to the second equation, that is the equation that eventually, when you introduce this mean field approximation, it's an equation for the static structure factor. That equation included on the right-hand side a bracket that was the structure factor minus the inverse of the second derivative of the free energy, which depended on wave vector. If you make an expansion up to quadratic terms in the wave vector, then you get precisely the basic equation of a spinodal decomposition, the early stages of a spinodal decomposition. So these two equations connect with, in one case, with density functional theory through the first one equation, and with a spinodal decomposition with the second equation. I hope that I...
Yeah, if you get the nonlinearities of, say, the Ginzburg functional, then that's nice.
Yeah, and something that I should stress is that in Ginzburg-Landau theory, you are only talking about long wavelengths. You cannot go to the details of the main peak of the static structure factor. And we know how to incorporate that. It is already built in the equation that I mentioned. Let me, I have a question because precisely this mobility, this local mobility, B of R and T, to some extent, or even better, the local density. The local density, let's say, if you are close to the critical MCT transition, then or near, then the distance from that is the sigma in both Thomas and Tommaso's presentation. And they talk about fluctuations, spatial fluctuations of that parameter. But in my language, that would be the local density itself. So the final part of my talk, I said, in principle, at least within a linear approximation for the first equation, we can calculate that. It's not a question, it's just saying, I'm very curious to see if that really will connect, if with this full theory that has heterogeneities, will we be able to connect with Tommaso's beta relaxation and with Thomas. I don't know if somebody wants to comment on that, because I cannot even pose the question, but it seems to me that our local density field that we illustrated with this in the case of spinodal decomposition, that field is probably the essence of heterogeneities, and the corresponding field for the mobility would be precisely the dynamic heterogeneities. Would we go in the right direction to describe dynamic heterogeneities by looking at the solution of this more complete equation that for the local density?
It seems to me that it is just the level of description of these heterogeneities and so on. I mean, these are two ways of estimating these heterogeneities as far as I could understood Tommaso's and Thomas' talk. And I actually wanted to ask Tommaso, let's say, I mean, considering the theory that you presented and so on, and let us say that for a finite dimensional system, 3D or whatsoever, thinking on these diagrams where you show the emergence of this kind of heterogeneities and so on, would be possible, for instance, to take that information to reconstruct, let's say, configurations in the spirit that Magdaleno showed, like putting the emergence of this kind of well-defined distribution of heterogeneities and so on to more or less represent the system in a, how to say it, graphical representation, to use it, for instance, to describe processes just as interrupted spinodal decomposition or things like that? Or would you say this is more like spirit to put these heterogeneities at the level of alpha relaxation times and things like that? I'm not even sure if I explained myself correctly.
Okay, no, I think maybe that if I understand correctly, maybe the second, maybe the second alternative. I mean, okay, well, first, okay, one thing that I would say is that really that kind of description, that the plots that we are plotting must always be intended as in a coarse grain description. So